Okay, question on light and waves, question 5. Radio station transmits on 97.4 megahertz, so that will need changing. So multiply by 10 to the 6. Hopefully you remember we learned nunc, and then our SI unit, and then K, M, capital M. The other one's a little m, G, T. Please make sure I'd write this as soon as you sit in the exam. I just write this on the front because that's all your unit changes done. So nano, micro, milli, centi, kilo, mega, giga, tera. And I told you to learn 10 to the minus 2, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12. And all we've got to do is then, if I'm going to the SI unit, multiply by this. Or you also learned to divide by a 1 with 2 zeros. Horses for courses, you pick what's best for you. But yeah, that's a good tip. Write that as soon as you get into the exam on the front, and then any higher tier unit changes are done. So to receive the waves, the area needs to length equal to half the wavelength. So half, I'm just going to circle that. You're going to try and catch me out with it. Calculate the length of the area needed, and it actually gives us the speed. Please make sure you know that celeritas C equals 3 times 10 to the 8, because they could have missed that out and you've just gone, I don't know what I'm doing. So our memory method for this, foxes stab wolves, and then we're away. So W, that's what we're trying to find out, equals speed divided by frequency, or velocity divided by frequency. Remember, they could put that as frequency equals velocity over lambda. So shove the numbers in. So 9.74 times 10 to the 7 is what I'd get if I times the megahertz by 10 to the 6. Put it in. There's my wavelength. So I've worked out it's close to 3.1 meters divided by 2, 1.54 meters. Done. Next one, your favorite, measuring refraction and measuring critical angles. So it says describe how they could do it. So I'm going to draw on here. Well, the first part is we can see they've drawn the normal line, and to measure the angle you've got to state that the angle's from the normal. You've got to state that. So we always measure the angle from the normal. Well, if I was doing this in the lab with my groups, it's that put an X here, put an X here, because now we know where it enters and where it exits. We've got the normal mark. They've done that for us. We'd then take the glass block away and we would draw a line here. You can see the normal and the angle of refraction. There's the angle of incidence, theta I. This beauty here, that angle there, that's the angle of refraction. And I would get rid of all of the gubbins and I would show it on the diagram. Oh my God. I'd show it on the diagram for the examiner to show you know it is this angle here, and I'd label that as theta R, and this is theta I. Angle of incidence, angle of refraction, and it's that from the normal. So now we've just got to put that into words. So mark with an X where the ray entered and left the glass. Remove the block and draw a straight line. See the diagram above. Obviously you would have used a pencil and a ruler. Use a protractor. Oh, I didn't say that when I was modelling it. Yep, so you've got to say what you're going to measure the angle with. There's the key word there. Use a protractor to measure the angle from the normal, as seen here. Ta-da! On to the next one. Figure 6 is a simplified diagram to show radio waves from a transmitter moving upwards. They meet the boundary, and we can see what's going on here. So we've got the upper and lower layer. We can see, well, this wave has been refracted, so I'm going to have to mention that. And that just means that it's changed speed at the boundary. So delta, I'll put delta V to be fair. And then this one's been reflected. So speed's going to be the same. So it's going to be the same velocity there. But we know this angle, theta I, equals the angle of reflection. We know those two angles equal each other. So we're just going to tidy all of that up. And one of the reasons we use radio waves for communication is we can bounce them off the atmosphere, which is kind of useful. And because they don't have a lot of energy. Clearly, communicating with satellites, this is going to be rubbish because a lot of our energy is going to be reflected back to Earth. Thus why we use microwaves. So your explanation needs to refer to changes in direction and the speed of the waves. So the crucial part is, well, the refracted one's changed direction. Why? Because it's slowed as it's hit the boundary. And the reflected ray it has bounced off the upper atmosphere, and the angle at which it has an incident with the boundary is the same as the angle at which it's reflected, but that does not change velocity, it's just bounced back. So wave P is refracted, mark, as it's been slowed at the boundary. I told you to get a pencil sharpener or a rubber and do your little car thing. So we're going to go, I'll draw a little car, side A, side B, I said to label it. Side A will hit first, this side will slow down, and therefore it's going to bend towards the normal. I think I've almost also taught you MTLA. So if the substance is more dense, it goes, imagine that's the normal, let's put the same normal there, it'll go towards the normal. If it's less dense, it'll go away from the normal. I hope that makes sense. So MTLA will help you. Wave Q has been reflected. The angle of incidence equals the angle of reflection, and the speed is the same. So we've done what we wanted. We've talked about direction changes, how we can measure those direction changes, why that happens in terms of the speed of the waves. That's that one done.